Hi there, and welcome to the Commercializing Quantum Insight Hour, where we'll be answering the question, what will it take to create the quantum internet? It's an honor to be joined by Krysta Svore, the VP of Quantum Software at Microsoft, Stephanie Simmons, Chief Quantum Officer at Photonic Inc., a job title I expect to be hearing more and more of in the years to come, and David Shaw, Chief Analyst at Global Quantum Intelligence. Hello, all.
Hi, Jason.
Good morning.
You all know this. The audience perhaps already knows this about me. I like to start with definitions. I really think it helps sort of clear the air, make sure we're all talking about the same thing, and it probably reveals what it is that we are going to be sort of talking through here. So nice, easy 10-point starter for everyone, perhaps in turn, about just get us on an even playing field as regards where quantum computing is at generally before we talk about where it's headed. Krysta, would you like to start just briefly? Where is quantum computing right now in your mind?
Yeah, so we're really working on building quantum computers so that we can accelerate scientific discovery, right? And so we're on path. We have quantum computers today, right? At Microsoft, we offer those through the Azure cloud, and also they're integrated into Azure Quantum Elements, right? So really, we're thinking about using quantum computers, right? Currently, they're at what we call level 1. Those are foundational quantum machines. We need to get to level 2, where they get larger and use what we call logical qubits, and then on to level 3, where you have scale and you have a very large scale quantum supercomputer that's integrated in alongside AI and HPC. So today is really about we've done that integration with AI and HPC, and we want to work to scale up our quantum machines, and we want to build out the quantum ecosystem, right? So in addition to having scaled up quantum machines, we want to have a quantum internet that can ultimately enable connecting across those machines and across different things like sensors and so forth. So that's kind of the state of where we are today.
Okay. Stephanie, where is the field at this moment in your mind?
Oh, well, Krysta absolutely got it right. There's a lot of exciting progress. Maybe I'll just speak to the pace of progress. Things are moving very, very quickly. And there's a lot of applications that we know of, if we've done the quantum resource estimation, as it were, figure out how many logical qubits are necessary to deliver something valuable. And it is in that early supercomputer phase of that level 3 that Krysta pointed to. So absolutely spot on. I think what's really exciting is there's a little bit of an accelerating interest in that ability to network these together, and that's the basis for this call, is this so-called quantum internet, but really it's networked quantum computing and what that enables. So I see quite a bit of acceleration towards unlocking that horizontal scalability as an approach to that supercomputer phase and beyond, and so that's a very exciting time to be a part of quantum technology development.
Nice. And David, from your standpoint, where do you think the field is, or anything that hasn't been picked up yet that you think we might be missing?
Well, I think one of the things that makes the question of definitions in the field interesting in itself is that when you speak to different players across the field, they do have different emphases, and it reflects their worldview of where the value is going to come from. And there's certain players in the field that are very full and squarely focused on large-scale fault-tolerant quantum computers as being the way we'll realize the value that we really see there. And there's other players that see that as well, but they actually have a more aggressive schedule, perhaps, of what we might be able to do with early modest-scale fault-tolerant machines. And then there are other players that yes, they recognize that's the destination of the journey they want to see, but they're still more bullish about what we might be able to do with early so-called noisy intermediate-scale quantum devices. And while it's very healthy in the market to see players all with these different views on the roadmap forward, as an audience and as the listener, you have to be alert to the fact that there are different people saying different things.
And this is something, in fact, that came up during the conference earlier in June about essentially the death of the noisy intermediate scale quantum computing sort of as an idea. Now, perhaps I have a very particular audience here for this question, right? But this is not where you guys are focused, Krysta and Stephanie, on this is for a while. even as late as last year's conference, there was talk about how to squeeze some value out of those machines. You're kind of thinking sort of beyond that, or may I say instead of that, only at scale. We have to also be careful when we use the word scale around, I suppose.
Yeah, I think
Sure.
ultimately, Jason, oh, sorry about that,
Please,
Steph.
Krysta.
I think ultimately, Jason, we want to see advantage, right? We want to see value, a mixture of scientific value over to commercial value coming from quantum computers, from the ability to connect those quantum computers, right, and connecting quantum sensors, right? So from that quantum ecosystem, we need to see quantum advantage, where we have something that we can't do classically, that we can do better than we can do classically, that we can do differently than we do classically. So we really need to see something, new, better, different, coming from that quantum ecosystem. And so that's our focus. And we believe that to get there, we're going to need to scale up, right? And scale up such that we have the ability to apply what we call quantum error correction, that we have the ability to drive longer and longer computation that becomes and remains reliable now, as you increase that computation you want to do, right? So ultimately, you want to be able to keep quantum computers and the connection between quantum computers, if you're also leveraging that, you want to keep it alive for a long time, say, a month of computation time. And to do that and get advantage from those machines, you need what we call logical qubits. You need quantum error correction. And so that's where this idea that level 1, noisy intermediate scale quantum computing, right? This is where you're using physical qubits directly. We believe that is not going to give you this commercial quantum advantage, right? For problems that we really believe are going to be useful for the industry, as well as be able to be solved, say, within a month or less. So it's really important we get there to make this technology super valuable, to drive that value from this technology. And that's going to require transitioning from these physical qubits to logical qubits, which ultimately requires more physical qubits, right? So we need to be able to scale up.
Right. And Stephanie, you had a thought on that as well?
Yeah, I just wanted to build on that, which is absolutely correct. I think it's important to recognize that we're in a special situation where we can know before these large-scale systems are built that commercial value will exist, right? We can run the pen and paper algorithms, quantum algorithms, and you require a certain number of reliable logical qubits to be able to deliver something valuable. That's great. And that, in some sense, those systems that can deliver large-scale, reliable quantum algorithms could do anything else that level 1 and level 2 could do, right? So if there ends up being unknown algorithms that emerge in this kind of phase 2, stage 2, level 2, like picture of quantum, where you have a small-scale number of reliable qubits, awesome. But the large-scale systems can do that too, and with space-time trade-offs can even maybe do it faster, right? So there's an opportunity to really hone in on what it takes to deliver level 3, phase 3, like ultimately large-scale systems, because those systems are going to be the ones that stand the test of time going forward and can deliver all the value that does exist on all the stages along the way. So that's why it's really important to double-click on engineering for that long-term success.
Okay, so for the purposes of our discussion today, then we are talking about the further up the phases levels, right, to big scale computers. We leave NISC behind for the moment. Fair enough. Last thing, if you'll indulge me on definitions, we're here to ask what it will take to create the quantum internet. What's that? What do we mean when we say quantum networking? Let's go through again one by one. Krysta.
Yeah, well, so quantum networking, I think we think about this really as a capability, right? A resource you can bring to different types of technologies or things you want to do in the quantum ecosystem. So what I mean is we think about this as the ability to distribute entanglement. So when you're networking, you're sharing this entanglement, you're spreading entanglement. You can do that within a quantum machine, right, within a quantum computer, where you're sharing that in a more, maybe local way, but also in a, a longer distance way. So you could think of that as enabling distributed quantum computing. You can think of that as enabling maybe a larger quantum supercomputer. And then additionally, you can think of that as a means of communication, which may match or be analogous to our classical internet, right? Where now you have a quantum internet and I can share quantum information across this internet. I can share it between, quantum data centers of the future, right? So there's different applications, different ways to think about quantum networking. And that quantum networking also, you can bring in things like quantum sensors, right? That actually have quantum data. And then you can share that quantum data, for example, with quantum machines. So the quantum internet is really, or quantum networking more generally, can enable something like the quantum internet, but then it also can enable something like distributed quantum computers or even a large quantum computer where you have that networking within the machine itself, right? So different applications here. But at the core, you're sharing this entanglement, you're spreading or distributing entanglement to enable this network.
Right. Stephanie, anything to add to that?
Yes, please. Krysta is absolutely spot on. That's absolutely the right way to think about it. What I would add is that this merger of thinking about distributed quantum computers is essentially a bunch of qubits on the edge of a network. Like, it's really kind of inverting the way we've been thinking about quantum computing development to date, where people have been quite constrained by the size of their box to have the really perfect environment needed to do error correction and beyond. And so kind of shifting gears, and we heard it very much at the Economist conference, this drive towards networked quantum computing, because once you're out of the box, you can enable not just, yes, distributed quantum computing, but all these other applications like blind quantum computing or QKD networks over longer distances or with larger user counts, or basically any quantum application beyond single point quantum sensors. I think it's all actually going to be powered by entanglement, and that is, I think, the right resource to be thinking about. And instead of thinking of it like, the word internet makes you think that you're sending packets, right? Like you're sending data, but really it's closer to like an electricity grid, right? It's a resource that kind of gets shared around, and once it's there, once it arrives, you can consume it for any of these applications. So getting really good at that means that you could plug into everything going forward. And so that's one of the things that here at Photonic we've been really double clicking on, really focused on entanglement distribution as the core thing to really optimize for, because that does enable this broader set of not just local, but distributed and ultimately global applications for quantum technologies. But I know David has a view on this one, so
and I'm going to seek it.
No, I think it's useful in this question about defining, understanding what people mean when they talk about quantum networks, the quantum internet. I think it's useful to understand that, I would say there's broadly three different communities that have come at this from slightly different positions, and it reflects in how they speak about it. I think there's one group which comes from a quantum communications background, which has traditionally looked first at cybersecurity type issues. It thinks about extended networks. It's focused on QKD, quantum key delivery, as an early potential application, and then more sophisticated. So it's thought about, how do I do security type protocols over a long range network, is its traditional focus. Then there's another community, which is really the quantum computing community, that sees networking as a way to do modular scaling with a local quantum device. And so they naturally focus on networking within the data center, if you like. So it's much more of an emphasis on short-range networking. And in a formalized sense, it becomes what we call distributed quantum computing. And that can mean a group of modules, but still in the data center. And then there's a third group, which is really the quantum sensing community. And it's a shame this community doesn't really talk about this as much. It hasn't been engaged as much about this. And that's a shame, because as Krysta was saying, there are really interesting advanced applications to be got from ultimately networking those quantum sensors together. So when you talk about this, quantum internet, quantum networks, you have to realize that there's these three different traditions impinging into what's then the same technology to allow this to happen. And at the heart of that technology, as Steph was saying is entanglement. It's about networking that entanglement across these different nodes.
Well, I'm interested in the degree to, if you were to come at this cold, this is going to look to you just like a quantum analog then of the things we already know about, right? A local area network so that I can send something to my printer, and internet so I can get something, send an email to my grandmother, whatever. There is laid on top of that high performance computing, high performance quantum computing, essentially distributed quantum computing, no different, no, they're like perfectly analogous. How does that fall short as an analogy? Why is this different? Why is the being able to send around entanglement empowering in some way? I don't think that's immediately obvious if you think about the way we've all been talking about quantum computing for all these years.
I can have a go.
I bet everyone wants a piece of that one.
Oh, sorry. I can wait my turn as well if you'd like.
Please, Stephanie, go.
So it is kind of the secret sauce that differentiates classical computing from quantum computing, right? If you take a look at all of the possible quantum states, they're actually a superset, to use the math term, of classical computing. And the big differentiation between the two is entangled quantum states. And it ends up being the kind of basic building block like a NAND gate, right? Just like you see with classical. So the analogy is actually quite precise. But I wanted to come back to David's point. The fact that it took this long for us to realize how precise that analogy was is a little bit to do with the history of the development of the field. Because in some sense, the thing that's been limiting the scale for quantum networks to a set distance or a set user count has been the lack of its integration with what's called quantum repeaters, which are actually just small-scale, reliable quantum computers. And the same thing with quantum computers. Like in some sense, there's actually been a lot of small, high-performance systems that have been demonstrated in academia and otherwise. And we just need more of them. And if we can network them together and have an easy way of networking, and not all of them have an easy way of networking, but if we could network those together, then we could deliver some of this commercial value sooner. And it's been kind of a slow realization that the merger of these two things can unblock the other in some circumstances. And so it really has been a very human endeavor to driving these communities together over time to see these to see how precise this analogy actually is, Jason.
Right, but again,
Jason,
put myself in the shoes of. Go on.
Yeah, I wanted to come back, but I think there's a danger with this analogy as you paint it that I would want to point out when one talks about, so it's a bit like local area networking. It's a bit like adding on the ability to send any. There's a danger that people grasp that conventional networking terminology and they think they've understood more than they have about the potential that this new quantum technology brings. And I think really I'm rephrasing Steph's point in slightly other terms. The adding entanglement to the mix gives that network capabilities that really weren't there before, and in an exponentially improved way. When I take two quantum devices, when I take two conventional computers in the data center and I network them together, I've got two conventional computers networked together. When I take two quantum devices and coherently network them in the data center, I exponentially expand the computational space they can access. It is not a small deal. It is a massive deal, and it's a massive deal that goes to the heart of the power of quantum computing. So if I take two quantum devices separated by 1,000 kilometers, joined together by that extended network with quantum repeaters, but they share entanglement, now I have a very unique resource that lets me demonstrate, regardless of what adversary I might face, that I have a secure connection, that I can perform secure, information theoretically secure cryptography. And if I have two sensors that are joined, that are part of a conventional network, I'm limited in how I can scale their sensitivity. It fundamentally, it scales by 1/√n. Whereas if I do that with coherently networked quantum sensors, I get an inherent advantage in how their sensitivity scales, and I get an exponential advantage in the machine learning I can do to learn their response behavior. And these are radically improved capabilities that come from that networking, the entanglement. This is a more powerful concept than conventional networking.
And if I
Okay,
can
I have a new
add
strategy.
something, oh,
Sure, Krysta, go on.
I just want to add, what David's pointing out, what Steph pointed out, right? In using the term computer and internet, right? We think, oh, this is like a better version of the classical, and maybe it replaces classical. And I think it's really important also to recognize, right? This is about finding, entirely new capabilities that we cannot do classically, right? It's about finding problems that are intractable classically, right? Not possible classically because the solutions take billions of years or lifetime of the universe timescales, right? It's about the fact that we literally can't share information, right? In this way, right? So it's not going to replace the classical internet. We still have the classical internet. We still have classical computers. You still have your cell phone, right? Or your different devices. This is about bringing net new capabilities forward that are not possible to compute classically or communicate in this way classically, right? And this is really important because the way we're going to use the quantum capabilities, whether it's a quantum internet, in addition, right, the quantum computer, right, at scale, right, it's going to be used alongside what we have classically, and we need to integrate it the right way, right, where we leverage the cloud, we leverage HPC capabilities, we leverage AI, and we leverage what we get from quantum computing and quantum networking in a net new way. So I think it's really critical to remember we don't just throw away and replace, right? This is alongside and integrated with the technologies that we already know and love today.
Right. So it is an
Maybe
and
I'll jump
not
in
or.
I'll jump in with just a quick worked example. Maybe it's for the audience here, just to absolutely agree with what was said. It's new capabilities that we're unlocking. So it's not going to discount the fact that we have existing capabilities, which are outstanding. But here's one example of entanglement that you can do, but you just can't do with classical information. If you distribute entanglement between two sites, that entangled pair, that two pairs single pair of entangled information doesn't actually carry information really per se. If you were to measure it, it's uncorrelated. It's a random outcome, let's say, but it would be correlated between the two. But you can use that once you've distributed it to teleport information. You can teleport information from one site to the other, and that information actually never travels through that intervening space. This is like a quantum 101 example, but it's just to show that, when you have new laws, you can use new capabilities. And yes, some of those can be pointed at computing, but some of them can be pointed at completely different applications as well. Once you can harness these new laws, which ultimately all kind of stand on the shoulders of entanglement distribution. Thank you.
I can hear in my head the sound of lots of the audience nodding along, and then the other part of the audience having its mind entirely blown. Look, we got that far by me saying, it's just a local area network, isn't it? So that's my strategy next time. I'll just say that, then I can be corrected. We get right to the heart of it. The point here is, it sounds to me that I used to think about classical and quantum computing in terms of there's the computing bit, there's the CPU, there's the motherboard, and then there's the network, there's the bus, there's the wires, there's the network, there's the Wi-Fi, what have you. This is a notion where it's not a matter of some computing and some networking. It's that the network is part of, if not itself, the computer. Nodding. Good. Okay. We have defined all that we need to do. We haven't even used half the time yet. I suppose then we should kind of move on to the question then we're here to answer. What will it take to create the quantum internet? Why don't we start with where things are now, the state of the art. If your best hope for this is and completely networked, every quantum computer in the world networked together, like we're scrabbling around in the dirt right now. Where are things as regards networking? Who wants to begin?
We all do.
I'm going to suggest Steph should begin because, recently, as some may already know, right, Microsoft and Photonic have this co-innovation collaboration, and recently Photonic had a wonderful, large step forward in this regard. So I think Steph should share this result in terms of the state of play today.
There we go. Steph?
Excellent. Well, thank you. Thank you for that setup, Krysta. But I would say we are standing on the shoulders of giants here. So I would say that networking quantum systems is not easy. Actually, it's something that you have to engineer into the very, very basic building blocks of what you're doing, because most quantum systems, to perform well, need to be extremely isolated from basically everything. That's how you can hit high performance. And so there's a small subset of quantum systems that natively communicate with photons. And I'm going to assert, although there are other methods to do so, but I'm going to assert that you really do want photons to be the basis of a large scale network, because if you can click into that larger distance, the ease of networking using telecom light or telecom wavelength photons is just going to extremely outpace any other means of connecting quantum systems. So there have been a number of demonstrations, a handful of demonstrations in academia over the years, showing these really basic building blocks. But we were excited to share with the world that with our T-center qubits, which are a form of qubit that talks natively to telecom light, which is almost unique in that regard, which we only discovered 4 years ago. We've already obtained the ability to perform distributed quantum computing or networked quantum computing using those basic ingredients. And again, early proof of principle, but it's moving very quickly. So if I could just two sentences on elaborating there. What we have are spin qubits. So these are qubits in silicon, which have in the history of quantum technology development themselves set all kinds of world records, right? So silicon spin qubits are excellent individual qubits beyond being natively integrated into a very promising commercial platform for manufacturing. But what's different about these, and it's different from any other spin qubit in silicon largely, is that yes, they do emit spin entangled photons. So what we were able to share with the world was the kind of standard protocol for using that spin entangled photon from two different T-centers, two different spin qubit centers, over two different computers, each having thousands of qubits apiece. They would emit light, and that light would interfere. And so those qubits are entangled. They don't need proximity. So that means you can do things like print 1 million of them and pick your favorite 100,000 and then use them to network into your larger scale system. So it has the density of scale, vertical scale in the limit within individual chips. But yes, the ability to rack mount, we can already take multiple cryostats and perform computation with them together. So it's a very exciting first step, I would say, to kind of show all the basic pieces are working for a distributed quantum computing architecture. And I feel like there's going to be increasing attention in the industry, and maybe David could speak to this, towards that kind of unlock for horizontal scalability and ultimately the large scale, ever larger scale networked quantum computers will want in the future.
Right,
Well,
I was going to go to David because
just one thing on why we're so excited about this technology, right? Because as Steph mentioned, it uses telecom wavelength, and so this means it can be integrated into your everyday operating environments, right? You take Azure, right? You take data centers, you take the networks that all of the fiber, right, that we're using now. It can be integrated right into that environment. And this is huge, right? This is a differentiator to the other technologies, other approaches to this, right? Being able to integrate into your everyday operating environment, to your existing data center capabilities, right? That's critically important when we look at bringing this technology, right? We want to integrate quantum internet, quantum computing alongside AI and HPC. And so having that just match up so wonderfully is really key.
And David, maybe for a wider picture there.
Yeah, I think one of the things I think we all recognise that the demonstration that Photonic Inc. have just performed, and its broader work with Microsoft, focuses at really the cutting edge of the entanglement distribution part of quantum networking. It's probably worthwhile though to remember, and the members of the audience will hear other people talk about quantum networking. Just let's remember the context that that's being developed. There's a lot of players that have developed what are called prepare and measure quantum networks, where they're not distributing entanglement directly. They're doing a lesser preparatory task, which can be used for some applications. China have been very notable at demonstrating very long-range prepare and measure networks and using them for quantum key distribution. They've done quantum key distribution via satellite and also distributed entanglement via satellite as a demonstration. Europe's had a very big push through OpenQKD, EuroQCI at developing its own plans to roll out first more prepare and measure style networks. Now, it's important to remember that all of those players, I think all of those players would say that their long-term vision is also entanglement distribution. And some of this discussion is really about what's the best route to get there. Do I first build experience doing a lesser but long distance prepare and measure network, or do I make sure I can get these entanglement distribution technologies going first? And there's another balance as you look at how Steph has built out from what I need to do to network, locally for my entanglement distribution. See, people talk about the main technologies there, and it's important. I just want to put the statement about datacom wavelength photons being important, because in some sense, when the photonic community, the quantum photonic community talks about photons, it kind of implicitly means photons in the optical and infrared range, including in particular the O band and the C band for datacoms. But remember, photons are also, when you go into microwave range, they're also photons in a physics sense. And there are people that are trying to join their quantum computers together, their modules of their quantum computers together via microwave domain links. And you can get into a full hour debate about the pros and cons of all of that. But one of the things to bear in mind, and I'm trying to frame the point that Steph and Krysta have been emphasizing, if I can use photons that happen to be in a convenient datacoms band, an O band, a C band, to do all of these things, then I'm potentially onto a win-win, because I can potentially use that same interface, those same photons to do local modularity in my distributed quantum computing, and I can potentially also use those same interfaces to give me a route out to connect into those wider data sets. So it's not the only way to make it work. To do it like that. But if you can make it work like that, you're potentially onto a real triple whammy win of being able to link all of these things together. And that's why it's so exciting to be talking about these datacom compatible wavelength photons.
No, and this is in large part, I think, why there was always such a strong push for photonic computing, right, as opposed to other modalities, and trapped ions, neutral atoms, that sort of thing. Yeah, but if you could do it in photons, and the talk of, not even to speak of manufacturing or what have you, so that all makes a great deal of sense. I suppose what doesn't, in light of the conversation that we've had so far, is you say that there are plenty of people dealing with quantum networking, but they are not actually distributing the entanglement, which we have learned already in these minutes is a grand resource and really changes the game. I suppose I'd ask, and I, with all due respect to people who are working on those systems you describe, why not get the advantage of distributing the entanglement as that resource? I mean, doesn't that look like the way to do it? The double, triple whammy you described, is that not just the way?
It would be, but it's more difficult. It's more difficult to get the range. And the people that have looked at prepare and measure technology first, it's really been about that you can get the range much longer, earlier, quicker, with less other pieces of technological kit you have to develop to make it work. So that's the trade-off. You can do commercial QKD now over prepare and measure networks. People will sell you a box off the shelf, and we're not really quite there yet on entanglement distribution.
But everybody who's on the call, or at least Krysta and Stephanie, you're hoping to get us there. So we arrive then at that really that the nub of the question. We have a sense for where the technology is, or at least the horse that you're backing. You've mentioned this sort of framework of phases or levels, but let's kind of dig into it here. What are the steps between where we are now and where you want to be when this really reaches its maximum utility? Krysta?
Oh, sure. Or Krista, go.
Stephanie, I don't mind, honestly.
Okay, sure. Yeah, so it really is about focusing on what matters. And what matters is not just scale, but also performance, right? You need to absolutely deliver both. And in some systems, you have to really think about scale in terms of the spacing of your individual qubits within one chip, and that really, really matters. And usually you're using proximity-based operations. And again, depending upon the platform, they need to become ever more perfect. And that's been the domain of some systems rather than others. So it's been a bit of an interesting shift as we've shifted from the NISQ phase or the NISQ level to this kind of early days in the reliable quantum computing level, because it's really been that performance combined with scale within a single module that's been unlocking those first steps. And there's been some results, not just with Microsoft, but with others over the past couple months, which is very exciting, seeing these kinds of single module platforms delivering things that we knew were going to happen, right? We knew this was going to happen, but it was just a question of when and what kinds of error correcting codes we actually want to employ, right? So there's a little bit of interesting dynamic there. When we're shifting into the supercomputer phase, it's taking that to a whole other level. And again, there's different ways of obtaining that. But I think one of the interesting things about thinking about a distributed framework is that we know that, at least from the classical hyperscalers, you always want a bigger computer. You always want to keep going, right? So that has the advantage that you can obtain ever more in the future, ever more performant quantum systems in the very, very largest sense in terms of running larger algorithms, let's say. But the need for performance is still absolutely there. It's absolutely there. But I would share that there's a bit of a different way of thinking about it when you're doing an entanglement first architecture rather than a proximity-based architecture. So when you're doing a proximity-based architecture, you're kind of stuck with what's there, and you have, depending on the platform, you can have crosstalk or other issues that you have to work with. But once you're thinking about a network of quantum systems, you just have a little bit more engineering flexibility. So I would say that it's all over yet, right? Like we're talking about forays into that larger scale architecture. But it's really important, and we agree with Microsoft on this, to work backwards from success, right? To know what a winning condition looks like, and then engineering for that and making sure that that's all consistent, and making sure that you don't end up delivering something that ultimately doesn't end up delivering customer value. So one of the worries, and it wasn't known in advance, but when people started offering access to phase one systems, they thought, okay, maybe there would be lots of commercial value there. And it wasn't known in advance necessarily if there was going to be a heuristic that emerged in that phase that would really move the needle for companies. And so it's also not clear in the small scale logical phase what sorts of applications, again, where you draw the line. But it'll be interesting to see when that advantage clicks in and when that starts delivering exceptional value for people. But we do know that it exists in phase 3, and that's why it's super important to really focus on scalability and performance.
And maybe more squarely from Microsoft's point of view then, Krysta?
Yeah, I think when we think, again, going back to what do we do, right? What do we want to do with these quantum machines and quantum networks? So when we look at the levels, right? Level 1 being foundational, these NISQ, noisy intermediate scale quantum machines, what can you do there in terms of this performance, right? Steph was mentioning performance. It's, you have, one fault in 1,000 operations, roughly, right? At level 2, you want to drive it, right? So when you move to resilient quantum computing and you're using logical qubits, what you want to do is be able to take that physical qubit and those physical quantum operations that, you have one in 1,000 are faulty. You want to get to the point where you have only 1 in 1,000,000 fails, right? And then drive it to only, say, 1 in 100 million, right? So level 2 is about getting to the point where we can do 100 million operations with only one failure. And then at level 3, we want to drive it even further, because for that commercial quantum advantage, for example, in chemistry, right, when you want to, compute something, right, some property of a molecular structure, you might want to understand the ground state energy so that you can more, better model a catalyst, right, an industrial catalyst, and then actually synthesize that catalyst, right? To understand that, you're going to need something, a qubit and a quantum machine, right, that can get you to, say, only 1 in a trillion operations failing, and even further out past that, quadrillion, right? You need only 1 operation in a quadrillion operations can fail. And to do that, you're going to need these logical qubits, right? You need to continue to drive that improved performance. It's when you get to that 1 in a quadrillion scenario that you have access, right, to being able to do this catalysis, right? These reaction rate models where you have, higher accuracy than you can achieve classically, right? And that's where we're going to start to be able to use that alongside HPC, right, integrated with HPC and AI, to really drive accelerated scientific discovery. Now, along the way, though, we have advantage coming already when we have only 1 in 1,000,000 failures, right? And so that happens at level 2. So, we're right on the kind of the cusp of showing that. And in April this year, for example, at Microsoft, we demonstrated with Quantinuum, another quantum hardware provider, right? We demonstrated a breakthrough in showing that we have logical qubits, right? That we have crossed that threshold, that divide between level 1 and level 2, and we are now in the era of resilient quantum computing. And so we are getting, we've moved the industry forward. We are at the place where we now can drive towards that, 1 in 100,000, drive towards 1 in 1,000,000, only 1 in 1,000,000 failures, and then beyond, right? But we do want to drive all the way to that 1 in a quadrillion scenario. And that's going to be, not every type of qubit gets there. Not every type of quantum machine is going to get to level 3, right? It takes a lot to scale up. And that's where the technology that Photonic has, right, that Steph's been talking about, it's so interesting, right? And it has a potential, right, because you have this silicon spin that's naturally emitting these photons that operates across telecom wavelengths, so our everyday operating fiber environment, right, and can communicate that way, share that entanglement that way, right, and that's how you can think about scaling up. So that's one approach. It's one architecture to scale, right? There are other scenarios, right? Our topological approach looks at a more monolithic system where you don't actually use photonic networks to scale up. But here's this other mechanism, right, where that conversion from spin to photon, right? In other systems, it is very hard, right? It is very hard to take your qubit platform and convert to a photon to enable that networking. But here's this natural way, right? Which is so cool, right? That you have this natural way of enabling the networking, and you can use that not only for a potential quantum internet, but also to look at scaling up the quantum machine itself. And so we really want to get to that level 3 scale. Again, 1 in a quadrillion operations is the maximum failure rate that we want ultimately.
Right.
Yeah, I'd like to elaborate some of the technology behind what Kirsty's just been saying, because I think it's really useful to maybe get a grip on that. And it comes down to understanding these quantum error correcting codes, how we use those to create logical qubits with much lower error rates. And when people have followed this type of podcast in the past, they've probably got an idea in their mind. Oh yeah, I've heard of this before. It's such an overhead. We need thousands and thousands of these physical qubits, and then they're made into one logical qubit. There's a great overhead, and a lot of that understanding comes from one way that we can do that quantum error correction, which is called the surface code. And the surface code is much the best worked out technique we have. It really is the old guy of quantum error correcting codes. It may be that is the way we have to do things, but the high overheads associated with the surface code are related to one of its features. It only needs nearest neighbor qubit connectivity to operate. Now, if you have an architecture, and there's two ways you can then try to improve that overhead that the surface code gives you. One is you can start off from much better physical qubit fidelities, and that's the approach that Microsoft have been emphasizing through their work on topological qubits, and which ultimately does become a monolithic qubit design, one of the very few still in play in the industry that could do it. Lower overheads because it starts from a much better fidelity. Or you can say, well, are there other error correcting codes I can use? And in particular, there's a series of different types, but one particular class that's got a lot of discussion at the moment, so-called quantum LDPC codes. And these are adapted from classical communication codes. But the key thing about them is they offer much lower overheads. We might be talking of a 1 to 30 rather than a 1 to 1,000 overhead. But they need more connectivity. They need connectivity beyond just the nearest neighbor qubits. And that's why some of these architectures that we're thinking about that introduce more enhanced network connectivity as they bring their modules together, they come with a very interesting plus that potentially they give access to these more efficient, radically more efficient quantum error correcting codes. And so it's very interesting to see the connection point here between what teams like Microsoft and Photonic Inc bring, because we've talked a lot about the physical technology here, but actually both teams are also very strong in terms of their knowledge of quantum error correcting codes, and that's actually a leverage here. You're really trying to leverage that insight, that thought leadership in what we might be able to do to map it onto whichever hardware architecture manages to deliver. So it's a very fascinating game of business strategy across the different layers of the quantum stack.
And
can I jump in?
Please.
Sorry. You're absolutely spot on, David, and thank you very much for flagging it. I would just add the sense of that is this is a very dynamic space. It's a very dynamic space because nobody was talking about QLDPC codes even really a year and 2 months ago. We were on stage at the last Economist event talking about that. And there's been this massive recognition across the industry that, yeah, you know what, if we can get this all to work, then this just does offer some performance opportunities, which is very exciting. But I think it's more just to talk about the fact that this is still an early technology. Right. So we're in the history where there's this Cambrian explosion of different approaches, and we haven't yet consolidated on one winning architecture like CMOS did for silicon or jet planes have done since compared to the early Wright brothers work. Right. So there's a consolidation of design that isn't yet happening. And so there's a lot of opportunity for disruption and for new ways of thinking in this space, and QLDPC codes are absolutely one of those. But it is the case that regardless of the code, if you're working with a distributed architecture, a networked quantum architecture, you can connect your qubits any way you want. Right. And so you have the opportunity to engineer for whatever code ends up being the superior code, which I think is a level of flexibility and versatility. It also helps with yields. Right. Again, you don't need when you're not working with proximity, you don't need everything working. So the engineerability of all of this will end up being a feature in the longer term conversation about what systems end up performing best in what settings. And thanks, Jason.
Sure thing. Well, what you mentioned there sort of makes me wonder about what the wider industry is like, I suppose. First of all, in terms of opportunities that may present themselves, the notion that quite simply a better error correcting code would change the game, right? or in terms of applications, the discovery of different quantum algorithms could change the game and so on. And so in that sense, it feels a lot more, I don't know, like an open playing field in some ways. But I'm just kind of wondering whether, in a more general sense, this move towards quantum networked systems changes the kind of the overall playing field for the industry. It has felt at various points that that a few sort of it would end up with some runaway winners. That there were it was a sort of zero sum contest between different platforms and just waiting to see who was going to win the contest. What does that landscape more widely look like?
Jason, can I very quickly come in on that? Because I think you gave a great list there, but there was just one thing missing from it. The other disruptive factor, and Steph referred to it earlier, is if you genuinely get to a point where it is modular scaling, where it's just about, the module works, you know how to network it, it's just about adding an extra module on, then suddenly that is disruptive in itself. All of those other things you listed, yes, add the modularity on, and that takes you into a place where it's much easier to engineer the scaling forward.
But is modularity not kind of implicitly part of the goal here? Or
surprisingly
is that?
I think.
Oh no, go on.
Surprisingly not. So just a fact, like there have been academic demonstrations and a few academic pieces of work that have advocated for this over the years. But in general, and I'll have David comment on this, the broader community is not yet centrally focused on that ambition. And so one of the reasons why we were excited to share with the world how quickly we've come in 4 years is because we also wanted to be first in the commercial setting towards that larger objective. It is the case that people have been very focused on trying to get commercial value in either phase 1 or phase 2, and in some instances have been absolutely kicking distributed quantum computing to the long grass, like just really saying somebody else will figure it out. Like we're waiting on somebody else to figure out what these interconnects look like. Maybe later we'll bring it in. And so treating it as a central challenge to be engineered has not yet been a widespread belief, but I absolutely see early signs that is shifting between on some platforms beyond just our own. So maybe David can back me up on that one, but that's the current state.
Absolutely, it's very real for us that the industry, and I think it does come out of that phase where everyone was, some people are still optimistic about NISC, or at least keep an open mind on NISC. But there was a phase where lots of people were bullish about NISC, and that led to people wanting to push as far as they can, as fast as they can, with the device they had in play already. So it was all about trying to get my device over a NISC finish line, and that meant trying to do it without bothering with the rest. But certainly, we echoing Steph's point, we recently published a major report, Scalable Quantum Hardware. And the reason we did that was to make the case for thinking a lot more about modular scaling. And it's certainly ourselves arguing that we have to think through the journey that the industry faces more in those terms. Because almost all roadmaps, actually, that's the way you have to go to get a seriously large machine.
If I could jump in on a piece here, I think what's important is to remember where we want to go, right? Like we want to get to that maximum of 1 in a quadrillion operations failing. For example, we want to get to level 3 where we have a quantum supercomputer, and there are different architectures, different paths to get to a quantum supercomputer where you have over 1,000 logical qubits operating with just 1 error in a quadrillion operations. That is ultimately what we need to achieve. And as we've spoken about today, right, a path to get there is to look at leveraging the distribution of entanglement to enable getting to that level of scale. But I want to think about, also, right, how does this all come together, right? As a customer, what do you see, right? Really under the hood, right? This is all going to be co-designed and built out for a customer and then exposed in a way that ultimately should be very simple, right? It should be easy to use and integrate with your workflows for the solutions you want, right? And so ultimately, right, at Microsoft, for example, we are looking at bringing the devices, right, that Steph has spoken about here from Photonic, right, bringing those devices into, for example, Azure Quantum Elements, right, where you bring in that capability of quantum computing. It's integrated with HPC and AI. And this enables you then to be looking at accelerating your scientific discovery, and especially in the space of chemistry and material science, where these problems to get high accuracy classically can take longer than the lifetime of the universe. These are intractable problems. And when you bring that together with AI, you have these very advanced capabilities, right? And already today we have quantum devices integrated in Elements, but the goal, right, is to get those scaled up and bringing this technology that we've outlined today in the work with Photonic, right, bringing that into Elements as it scales up will bring these new capabilities forward for that scientific discovery. But ultimately, you want to be able to study problems, right? You want to understand things like nitrogen fixation, right? Where, for example, this is how we produce artificial fertilizer all around the world. We want to do this in a more efficient way. We want to reduce the reliance on natural gas, right? On our natural resources. To do that, we need to be able to model molecular structures, right? All the electron dance that's happening there, we need to model very, very accurately. And we want to be able to do this for a variety of materials, a variety of molecules. And so it's essential that we scale up our quantum machines, right? That we get to the point where we have that commercial quantum advantage. And we're leveraging not only the quantum machine as, say, one of the layers or one of several layers in a full computational workflow, right? So the idea is that you have this workbench, right? Instead of just working at the in the wet lab, right? You can actually predict computationally a set of capabilities. And so, for example, in Elements already, we've looked at, we've actually had recently discovered a new battery electrolyte with Pacific Northwest National Labs, right? And that doesn't yet use the quantum machine, but the idea is that we could generate 32 million candidates, right? More candidates than ever before. Then you use a variety of AI models and HPC simulations to filter that down, right? To really get that down to just around 20 candidates. You look at those candidates, and P&L then synthesized one in the lab. We did this in a matter of just 80 hours to go from 32 million to a matter of 20. And then it took, a matter of months to synthesize it, but it worked, right? It's a real battery, right? It has 70% less lithium. And so this is amazing, right? The point is you have this platform for discovery, right? That operates in a matter of a week, right? You've done something that normally would take 2 decades. And so now imagine having a quantum machine in the mix, right? That's scaling up, right? Where you're leveraging the technology we've been talking about today, right? That adds this layer, this capability you just don't have classically, right? You will not have with all this classical supercomputers in the world, right? And so ultimately that's where we want to get, right? We want to get to the point where we are driving this new discovery with this technology alongside, right, these other technologies that we've seen as so disruptive recently, especially, right, with AI. So I think it's just an amazing, amazing path ahead for our customers worldwide, right, to begin, looking at how can you leverage these types of capabilities.
Well, this is exactly the question, right? I'm glad that the end user has appeared as a character in this story, albeit in the last couple of minutes that we have together. But I suppose that leads to a question with just a small amount of time to tackle it. What business leaders ought to be thinking about this now? We have established, without really giving a whole lot of detail, this is an astonishingly capable system. What we hope to get to, these network systems have capabilities far beyond, perhaps, other architectures. Okay, cool. Not clear if I'm in the business of logistics, if I'm in the business of any other business, really, whether quantum can do something for me. So with safe in the knowledge that this is pressing ahead, I suppose, let me give you, 45 seconds each. I'm in the audience, I'm sitting there, I'm not sure if my business can benefit, but I have been wholly convinced that this is really progressing, that there is great promise, that this is going to get somewhere. What should I be doing with that view? David, start with you.
Just one thing. David, go.
I've got two suggestions I would make to business leaders. The first is you're looking for a summer reading book to take with you on holiday. Take one of the good ones on quantum mechanics, an introduction to quantum mechanics, and try to learn about it. Now, what you'll come away with that with is it's the classic phrase: if you're not shocked by what you learn, you've not understood it properly. Now, then you'll get back to the boardroom, having come back from holiday, and you should put all of that out of your mind. Forget it. It's actually great stuff to learn because it is profoundly fascinating. But actually, entanglement's a resource. It's a resource that this new technology uses. And you've got to work out what that resource means to your business. Now, it may be that resource is just a background thing for your business. It may, they'll be using it somewhere, but, you don't really need to in your factories. But for some businesses, that'll be the case. Then there'll be other businesses where, well, actually, it's quite an important resource. And I have to care because if I don't efficiently use that, then I better have a procurement manager who's right on top of making sure we efficiently use that. But then there'll be other businesses where actually this is a disruptive resource which is going to change how you do certain value chain steps in your business. And if you're one of those, you've got to be right on top of it in the boardroom. Now, which of those three businesses you are, I don't know, but you as the business leader need to be very clear which of those three you are.
Well, that is a good setup then for two more very brief answers then. David has made it clear we need to look into this, how to go about looking into it. Stephanie, I know you wanted to jump in.
Sure, thank you. So I would just add that there is one application that will have a universal impact, and that is the exponential speed up for cryptography and the ability to break RSA and EDCH and a lot of the other algorithms that are being used to protect. Now, fortunately, there are NIST standards that are going to be coming out in the weeks and months to come that we hope will be able to withstand future quantum computers. But that is one thing that is unlocked by distributed quantum computing. And so it's one of these things that, I think that once the information is out there, that technology will go to the broader world. And we should make sure that we transition our cybersecurity now to a quantum safe algorithm in the hopes that these quantum safe algorithms, which have gone through rigorous testing with NIST, will be able to hold them together. I would also say that for some industries that really need that enduring long-term security, they might want to think about quantum networks. So quantum networks have this capability to prove whether or not an eavesdropper detected the transmission. And with that condition, you can have some additional layer of security beyond a quantum safe algorithm to secure one's data that you want to have withstand the test of time. And we haven't yet seen how that's going to shake out as a market yet. So it's going to be a really interesting realization when people realize that things like Shor's algorithm is actually more imminent with these new codes and distributed computing than you might otherwise imagine. If you have that ability to scale and the ability to use better codes and more than one approach to distributed computing could potentially or non-distributed computing could unlock this. Maybe thinking a little bit ahead in terms of how to protect your information might go a long way, regardless of what the other applications your business might be able to benefit from.
Right. Okay. So a view that at least in some way everybody needs to benefit from this. Krysta, it falls to you for the sort of last brief comment here. What would you say to business leaders and what they should do to make sure that they are on the right part of this wave?
Yeah, well, absolutely, agree with what Steph and David have outlined. It's very important, right, that everyone think about security, and it's critical to have a secure future. And Microsoft has a secure future program. The best way to protect is to move to the cloud, to move to Azure, right, where the security will be enabled, right, for you, right? You'll have the best-in-class security in the world in that manner, right? That is the best way to protect your data and your compute. And alongside, I want to emphasize that everyone will be impacted. Every human on the planet will be impacted by quantum computing. And this is because 96% of the world's manufactured goods rely on chemistry and materials science. And that is the number one application for quantum computers. Quantum computers are really good at quantum mechanics. And within these molecules, right, you have quantum mechanical calculations that we need to do in order to mimic that, right? And so it's really about modeling that, right? We want computational capabilities coming forward. So everyone in the world will ultimately be impacted. But I think, as of right now, we know that this is going to be game changing for computational science. And so if you're in that space, if your business is in that space, you should be looking at these, this technology, right? And Elements is a great platform for bringing that forward. Already, right now, you can have impact with that. If you're in another space, right, we don't know if it will offer, all the speed ups you might be hoping for example, in optimization, right? That may require a much, much, much larger quantum machine. So, there we work to discover that, right? We work to bring down the cost of the quantum algorithms, of the error correction, right? Scale up the machines. But if you're in that area of computational science, right, scientific discovery is needed for your business, this is a critical technology for you.
Great. Well, listen, apologies to you, Krysta, Stephanie, David, for keeping you a little bit late, and to the audience for doing the same for the moment. Thank you very much for your time, all three of you.